Welcome to this lesson on alkanes. In this presentation, we'll learn what alkanes are, how they are named, their physical and chemical properties, and the important reactions they undergo for the A-level chemistry specification. Course context and A-level specification focus, definition and key characteristics of alkanes. Alkanes are the first homologous series studied in detail and provide a foundation for understanding more complex organic reactions later, such as those of alkenes, halogenoalkanes, alcohols, and polymers. Alkanes are saturated hydrocarbons containing only carbon-carbon and carbon-hydrogen single bonds. Alkanes are defined as saturated hydrocarbons, meaning they contain only carbon and hydrogen atoms and have only single covalent bonds between carbon atoms. The term saturated indicates that each carbon atom forms the maximum number of bonds possible, with no carbon-carbon double or triple bonds present. As a result, alkanes are relatively unreactive compared with unsaturated hydrocarbons such as alkenes. Structurally, each carbon atom in an alkane is sp³ hybridized and forms 4 sigma bonds, giving a tetrahedral arrangement with bond angles of approximately 109.5 degrees. General formula and homologous series, epoch naming of straight-chain alkanes. The general formula of alkanes, CH, arises because each carbon atom forms 4 single bonds, and in an open-chain alkane there are 2 hydrogen atoms, more than twice the number of carbon atoms. Alkanes form a homologous series, which means they share the same general formula, similar chemical reactions, and show a gradual trend in physical properties such as boiling point as molecular size increases. Consecutive members differ by a CH unit, for example ethane, CH, and propane, CH. For alkanes, students must know the names and structures of the first 10 straight-chain members, from methane to decane. Each name is derived from a root indicating the number of carbon atoms, combined with the suffix ane to show that the compound is a saturated hydrocarbon. Straight-chain alkanes are named according to the number of carbon atoms. The first 4 are methane, ethane, propane, and butane. Longer chains follow the same naming pattern. Structural isomerism in alkanes, physical properties, and boiling point trends. Structural isomerism is introduced in the context of alkanes to show that compounds can share the same molecular formula but have different structural arrangements. In alkanes, this is typically limited to chain isomerism, where carbon atoms are arranged in different branching patterns. For example, CH exists as 2 structural isomers, butane and 2-methylpropane. Although they have the same molecular formula, their displayed and structural formulae differ, leading to different physical properties such as boiling point. Alkanes show clear trends in physical properties that are directly linked to molecular size and intermolecular forces. As the number of carbon atoms increases, alkanes change from gases to liquids and eventually to solids at room temperature. This trend is explained by increasing London dispersion forces between larger molecules with more electrons and greater surface area. Boiling point increases steadily down the homologous series. Combustion of alkanes, free radical substitution with halogens, detailed mechanism stages and exam technique. Alkanes burn in oxygen during combustion. Complete combustion produces carbon dioxide and water. This reaction releases large amounts of energy, making alkanes useful as fuels. Incomplete combustion occurs when oxygen is limited, producing carbon monoxide and/or carbon soot in addition to water. Carbon monoxide is particularly hazardous because it is toxic and binds strongly to hemoglobin, reducing oxygen transport in the blood. Free radical substitution involves alkanes reacting with halogens such as chlorine in the presence of ultraviolet light. UV light provides the energy required to break the halogen-halogen bond, forming highly reactive free radicals. The overall reaction results in the substitution of a hydrogen atom in the alkane with a halogen atom, producing a halogenoalkane and hydrogen halide. The initiation step involves the homolytic fission of a halogen molecule under UV light, producing 2 halogen free radicals. In the propagation steps, a halogen radical reacts with an alkane to form a hydrogen halide and an alkyl radical, which then reacts with another halogen molecule to regenerate a halogen radical. These steps explain how the reaction continues as a chain process. Termination steps occur when 2 radicals combine, removing radicals from the system and stopping the reaction. Crude oil, fractional distillation, and uses of alkanes, environmental issues and sustainability. Alkanes are obtained primarily from crude oil and natural gas. Crude oil is a finite resource formed over millions of years and separated into fractions by fractional distillation. Each fraction contains a mixture of hydrocarbons with similar boiling points and chain lengths. Shorter chain alkanes are used as fuels such as LPG and petrol, while longer chains are used for lubricants, waxes, and bitumen. Combustion of alkanes produces carbon dioxide, a greenhouse gas that contributes to global warming and climate change. Incomplete combustion can lead to carbon monoxide and particulates, which cause air pollution and health problems. There is a growing emphasis on sustainability, including the finite nature of fossil fuels and the need for alternative energy sources. Summary, required practical links, and exam tips. For A-level exams, remember the general formula, be able to explain trends in boiling points, write balanced combustion equations, and describe the mechanism of free radical substitution using initiation, propagation, and termination. To summarize, alkanes are saturated hydrocarbons with only single carbon-carbon bonds. They undergo combustion and radical substitution reactions, form homologous series, and show increasing boiling points with chain length. These are key concepts for success in A-level chemistry. Thank you for watching.